Okay. So in this example, we have a piston cylinder and it's got 4 pounds of water, and they call it a water substance. And whenever you see water substance, that directly means that you have to figure out if it's saturated or not. Who knows? And it's at 500 degrees Fahrenheit, and it's going to undergo an isothermal process, and the V will change from 1.4 to 8.6 feet cubed. And during this process, 675 BTUs of work will be outputted. And we are asked to find the final pressure in PSI and the heat transfer in BTU. Okay, so let's sketch out real quick what's happening here. We have two states. We have state 1. And in state 1, we know the temperature is 500 Fahrenheit. And we know that, what else do we know? The volume, V1, is 1.4 feet cubed. We don't know the pressure. We probably should find out. What else is there? We don't know the U, we don't know the H, we don't know any of that. But as far as the state variables are concerned, as that, you know, you think of like the PV, because in our T stuff, we have PV and T here, and we don't know, we know the mass. So the mass here is 4.0 pounds. And obviously peripherally, we don't know the U, but we could find that out. We don't know U1, we don't know H1. We don't know any of that. Maybe we will want it, maybe we won't. I don't know. We'll see. And what's happening is that this thing is changing isothermally. We have some sort of isothermal process. And as a result, we have state 2. And in state 2, if it's isothermal, that means that the temperature stays the same. So that makes our life easier. So we know that we have this at 500 Fahrenheit. We also know V2, they were nice to give it to us. It expanded, so now it's at 8.60 foot cubed. We are asked for P2, we don't know it. And the mass shouldn't change, nothing happened. It's a closed system. So mass should be exactly the same. And again, I don't know what U is or H is, I don't know. Maybe I want it, maybe I don't. And during this process, we also know that there was some work that was that was done, and it's 675 BTUs. Right, and as we are also looking for the heat. Okay, so I'm going to write down. Give me a second. I'm going to write down the first law. We also just to kind of reiterate, when work is done by the system, it's got to be positive. So that's why I kept it as positive. So we don't know what the Q is. Maybe it's 0, maybe it's not. Who knows? So we're asked for that. Okay, so obviously what I need to do at the end of the day, and I don't have all the information right now, is to do this. This will give me my Q. That directly gives me the Q. Well, I know W, that's nice, but I don't know delta U. So I'm going to have to figure that out. Okay. So since this is a water substance, it's not an ideal gas or anything like that. I can't use any equation of state. I have to use the tables. Okay. So what I'm going to do is the easiest thing to do is to go fill in what I don't know. So I don't know the initial pressure. I don't know the initial U. And honestly, if I know the initial U, I don't need H. I don't see any reason for H here. So I'm going to erase that. I'm not going to need H. If I know the initial and final U's, I can subtract them, multiply by 4 pounds, and I'll get delta U. That's great. Then if I have delta U, I have W, I can find Q. Perfect. That's what I really need to do. And I am also asked for this pressure. So we could figure that out by the by. Okay, so this pressure won't help us in the calculation of Q, but they're asking for it, so we can give it to them. Okay, So what that means is I'm gonna have to go to the table to find U here. So I specifically will, my goal, I have three goals here, I guess. Goal number one is to find U, little u1. I can find that on the table. Goal number two would then be to find U2. And goal number three is to find P2. And if I was asked for P1, I could do it too, but I'm not. But it's not a big deal. Okay, so I'm gonna go for state one and check that out. Now, when I'm looking at the tables, okay, saturated or not, I have temperature, I have volume, I have mass, whatever. If you look at the tables, I am not ever given the overall volume, the intensive volume. I am given the specific volume, right? It's always meters cubed per kilogram or foot cube per pound or whatever. So I want to find V bar first, which is pretty easy to do. Let me find V1 bar because that's really what I need for the table. V1 bar, well, it's just going to be V divided by M. It's going to be V1 divided by M. And I'm not going to call it M1 because M is not changing. And so I'm going to put, what is that? 1.4 foot cubed divided by 4 pounds, which is 0.35. Okay, so that's going to help me. Foot cubed per pound mass. Okay, so pound M for pound mass. So now I'm equipped to go to the table because I have the V bar as this, and I also know T1, which is 500. That was given to me. Okay, so let's go to the table. I have two options. This is saturated or it's not. So I'm going to go to the table and figure that out. This is water. And so there are three possible tables for water. So let's find them and use them. Let's see. So in my book here, they're earlier on. This is edition 6, 7, or 8, or whatever it is. Okay, so I'm gonna go for saturated water first. Why not? So I know from my question, let me just fix this focusing thing. Cool. So I know from my question that I have temperature 500 degrees Fahrenheit. Look, this is all in Celsius, so I'm not in the correct units. So these are all tables in SI units. I'm going to flip over to the blue tables, and that's going to be my customary units. There you go. So this is saturated water, liquid vapor, and this is in increments of nice temperature. So I believe table 3 will probably be in increments of nice pressures. But I have 500 Fahrenheit. I don't even have the pressure. So I'm going to go for this to find that 500. And when I do, it's right here somewhere. Okay, so right here. Okay, so I see here that my pressure, my volume, I'm sorry, just get that for you. I'm gonna write that down. My volume is going to range between 0.02 or 0.43 for the liquid. I'll write that down. So if it's saturated, my volume of the of F specific is 0.02043, and that's foot cube per pound. Okay, and my volume of the gas is 0.6761, both foot cube per pound, and the V that was given to me is 0.35 foot cube per pound. Okay, these are all foot cube per pound for all three. So can I use a saturated table? Yes, and I should, because this is between these two values. If it were not between these two values, if this value was smaller than that, I would use the liquid table. If this value was larger than that, I would use the steam table. So I'm going to use this saturated table to find my my U. We want U. Okay, so I was not asked for the pressure, but if I was asked for P1, here it is. It's just 680. I'm not asked for that. But you know, So we have that. So what this means then, the first thing to do, to remind you, so once you establish that you want to use the saturated table, which we just did, the first step is to calculate the quality. Okay, which again, X will be the thing you're given minus the liquid. I shouldn't call it G. They're both G. Sorry about that. Just V bar. The V bar that you're given minus, I guess it's V1, minus V liquid divided by V of the gas minus V liquid. Okay, so in this case, and I'm going to omit units just to make it nice and neat, it's 0.35 minus the liquid, it's 0.02043. And all this divided by this minus that, 0.6761 minus 0.02043. This gives me the quality of this particular system, which we find is 0.503. So that means that this in state 1, I have saturated water. About half of it is liquid and about half of it is gas, a little more gas than liquid, just a tiny smidgen more. So from the quality now, once I calculate the quality, I can calculate whatever the heck I want. I can find the internal energy, I can find the enthalpy, I can find the entropy, whatever. I'm looking for U for the internal energy. So I'm going to look for U1, okay? And the way we do that is we will say U1 is going to be 1 minus X times U of the liquid plus X times U of the gas. Okay, so it's right here, these two U's, the internal energy. These two are the volumes. You can see the header. These two are the volumes. These two are the internal energy. So I'm going to just put that in here directly. And that's why I needed X, so I could get that. So I'm going to put X is 0.503 for this, 0.503 here. And UF would be 485.1 and UG would be 1117.4. So U1 here is 1 minus 0.503. And again, I'm going to omit the units. And then at the end, I'm going to give it this unit here. Again, cut off. It's BTU per pound mass. That's the unit of U. So UF here is 485.1, and I should really write BTU per pound, but I'm trying to conserve space and be brief. 0.503 times the U of the gas, just times 1117.4, and you just punch that into the calculator to find U1, and you find that U1 is 803, and I'm going to bring back the units. These two units and this one as well is BTU per pound mass. Okay, so that's great. So now I have U1. Great. So I'm going to go write that in my little board here, which summarizes my system here. Okay, so in this case, let's see, I'm going to get rid of all this. I have U1, we just calculated that. That's great. U1 right here is 803, was it? Yeah, 803 BTU per pound. Okay. BTU per pound. Okay. Now I'm going to have to basically repeat my analysis and find U2, and by the by get P2. That will solve that first part of the question to find P2, but I also want to know U2, because once I get U2, I get delta U. Delta U is equal to Q minus W. Cool. So I'm going to go try to find my information now for state 2. So for state 2, again, you need to figure out your specific volume. And your specific volume is going to be V2 divided by M. That's going to be my specific volume here. And that's going to be 8.60 divided by 4. Foot cubed per pound mass. Okay, and this is going to be 2.15 foot cubed per pound mass. Okay, so what this means, so now I have a V bar. I have this, and I have a temperature here at 500. Both of those can go help me figure out which table I want to use. Okay, again, onto the water table. So my goal is to find if V bar for the saturated, if 2.15 it lies between the liquid and the gas. Let's see. So it's at 500. Again, it's isothermal. Again, it's the same exact page. At 500, I was at 0.02043 and 0.6761. So this means that it's not between them because I'm at 2.15. I'm higher. I'm over the gas. Oh, can't see my finger. I'm sorry. So 500 here is at the saturated liquid is 0.02043. The saturated vapor is 0.6761. And again, we just calculated this thing is at 2.15, which is much higher than 0.6761. It is not saturated. Which one is it? Well, if it's lower than this, it's a liquid. If it's higher than this, it's a gas. So superheated. So I'm going to go to the superheated steam table. Try to help me. Okay, so I'm going to flip over. Table A3 here for me, just so you know, is the same exact as my saturated water before, only here it's in increments of nice pressure. Okay, and this is atmospheric pressure. And I'm not going to use that because I know it's not saturated. Then I have here A4 here is properties of superheated water vapor, which is where we are. And so we know that the temperature is 500, and we know the volume is 2.15. Okay, so I'm going to go around and try to find where that is. So I know I'm at 500. So let's just kind of mess around and see what happens. So this is a pressure of 1 psi. At 1 psi at 500, my specific volume is 571. That's way high. I need to be at 2.15. So that's not good. I'm going to just kind of fuss around and see what happens. If I go down to 10 psi here and 500, my volume is still really high. It's 57. I need to be at 2.15. If I go to, I don't know, whatever, even here, 180. I'm just kind of messing around because I know the answer. If I'm going to 180 at 500, I'm at 3. That's closer, but I still need to go further down. So I'm going to go 180. I'm going to go 250. At 250 and 500, boom, that's exactly what I want. I'm at 2.15. I don't have to interpolate. That's great. So I know my final pressure is 250 psi. Great. So that gives me that answer here. So I'm going to put that in directly. My second pressure here, we just figured out, that's 250 psi. Great. And I need to find U2 here. We want that. U2, well, I'm going to read off directly. So at 500, my U is 1163.8, and it's BTU per pound mass. So at 500, I'm at 1163.8. 1163.8 BTU per pound mass. I'm doing this super slow, I know. And I know you could probably do it much faster. I'm just trying to be very thorough. Okay. Trust me, I know I'm slow. I would not be slow myself if I were doing it for myself. Really trying to explain it. Okay. So now I have, I wasn't asked for the P1, but we have that. We had that. We were able to get that before, just for completion's sake. What the heck was that? It was 680. whatever, it doesn't really matter. We don't need it for the calculations, but here it is. So now I have the states fully described for me. I don't need the H's, so I didn't put them in, but I could have. I don't need the entropy, so I didn't put that in either. But I have all the states, I have all the variables. Now I could probably use, now, once I define the state, my last step would be to use the first law to get whatever I don't have. Okay, so so looking at the question here, find P final, we found it, good. And then now we got to do is find Q. Again, to remind you, delta U is Q minus W. Okay. Big U is little u times mass. So this is the same as mass times delta U is equal to Q minus W. We have W, it's 675. We want Q. We have the mass, it's 4 pounds, and we have the change in internal energy, goes from that to that. Okay, so final initial. So to get the answer, the Q, I know that the mass is 4 pounds. And I know the change in internal energy is 1163.8 minus 803. And this is BTU per pound, both of them. Okay, I keep calling it pound mass, that'd be consistent. Okay, so that's delta U. Okay, M delta U. I'm looking for Q and minus 675 BTU. Do I have to do any conversions? No, because these pounds will cancel these pounds and I get the left side of my equation in BTU and my right side of the equation, this is in BTU. So necessarily this will be in BTU. Then you just solve for Q and you find that Q is 2118.2 BTU, meaning that this process requires an input of 2000 and so or so BTUs for this thing to work.